Thank you very much, Mathieu. Hello, everyone. Welcome from the lunch. First of all, thanks for giving me this generous time allocation to tell you a bit about the survey that we're conducting. Actually, we just finished collecting data for. It's called the Binarity at Low Metallicity Survey. It's a monitoring survey, spectroscopic monitoring survey of about 1,000 massive stars in the Small Magellanic Cloud. One of its goals, not the only one, but one of its goals is indeed to find black holes. So I hope you guys will find that interesting. I don't think I need to motivate too much why we care about massive stars at low metallicity. And we already heard talks, whether it's black hole mergers, special transients, the high redshift universe, little red dots and green peas and blueberries, and all of that stuff that we are observing. It would be great if we could study massive stars in a high redshift universe. This is a bit tough. We cannot really resolve the stellar populations there. But what we can do is try and find galaxies in a nearby universe which kind of mimic those conditions. Okay, so the galaxies that we're talking about are typically dwarf galaxies because they have these shallow gravitational potentials. They don't really retain a lot of metals, and they can help us trace conditions of lower metallicities. Probably the most famous examples for such dwarf galaxies are the large and small Magellanic Clouds. These are very nearby galaxies. You see it here on the x-axis, the distance. Metallicity is plotted on the y-axis. So the LMC is about 50% solar. It's not really that low. The SMC is already reaching 20% solar, so taking us closer, but not quite, at the conditions of the early universe. If we want to go to even lower metallicities, we'd have to go further away to galaxies like Leo P and Sextans A. But these galaxies are already 1 megaparsec away, making them harder to study. But worse than that, in color, I plot the star formation rate of these galaxies. Star formation rate is what dictates how many massive stars are going to be there. And if you look at the star formation rates of galaxies like Leo P and Sextans A, they're pretty small. Pathetic, I wanted to say, but that's maybe a bit insulting for them. So you have quite a few massive stars in these galaxies. If you really want to probe statistically significant samples, you want to go to a galaxy like 1/18, but that's 18 megaparsec away, and we cannot currently, with current instrumentation, resolve the stars in this galaxy, but only study it with integrated light. So looking at this kind of overview picture, the SMC is an obvious treasure chest, okay, given to us by nature. We want to be able to understand the massive star populations in there. If we cannot understand them, there's no point in believing models that tell us what happens beyond the SMC. So the SMC has been subject to various spectroscopic surveys and photometric surveys over the years. This is a very nice Helms-Russell diagram originally constructed by Varsha Ramachandran, showing us various populations on the SMC. We have the OB type stars, the red and yellow supergiants. We have the 12 Wolf-Rayet stars that are known in this galaxy. Now we have these few strip stars that were recently identified by Guttberg and by Drought. What we don't see, this is not really related to my talk, but I do like to highlight this, and this applies to any galaxy we've studied so far. We don't see stars in this region, in the so-called Humphreys-Davidson limit. Stars about 30-ish, 35-ish solar masses, usually we don't see them expanding to large radii. So if you're talking about black hole progenitors in isolated binaries, don't necessarily assume that they inflate to red supergiant radii. At least empirically, this is not clear. So we have all these rich populations, but one thing we don't have yet are black holes, okay? So far, 0 black holes have been reported. There are about 120 high mass X-ray binaries in this galaxy. It's actually a comparable number to the galactic population, which is a bit amazing in itself. I had a discussion with Tom Acheron about this, not today's topic, but no black holes so far identified. So is this what we expect? Not really. So these are predictions from the same people who gave you the famous 2% of massive stars host black hole binaries, black hole companions. Detailed models as well as population syntheses predict that those black holes should be there at least around massive stars. So the important assumption in these models, I would say, is that they assume that there is negligible or even 0 kick for these black holes. If you do assume that, you might expect 150 to 200 OB plus black hole binaries to reside in this galaxy. So this is one of the many questions that we had. when we designed this new spectroscopic survey. So this is a survey I'm leading together with Julia Bodensteiner, with many other collaborators, some of whom are in this room. It's called the Binarity at Low Metallicity, or the Bloom campaign. And it's an ESO-large program that is dedicated to monitor, spectroscopically monitor, precisely 929 massive stars in a small Magellanic Cloud. We're monitoring them for 2 years, okay? We just finished actually collecting the data. The monitoring campaign is 25 epochs, so we have 25 visits for each of these stars, with many, many goals, like deriving the orbits, getting the binary fractions, hunting for black holes. So I mentioned that we have quite a few questions that we want to address, and indeed in this talk, I'm not just going to talk about black holes, but also a bit about their progenitors. I think that if we want to understand black holes, we also want to understand the properties of their massive star progenitors. For example, we want to address the question, what are the initial conditions of massive stars at low metallicity? For example, the binary fraction. So far, we haven't really systematically probed the binary fraction of massive stars at low metallicity. We're extrapolating this from high metallicity results. Are they even commonly in binaries? What are their orbital parameter configurations? What is the initial mass function at low metallicity? We want to address all of these questions. We also like to say in our field that binaries are the best single stars. We like to use binaries, first of all, because often we can tell whether they interacted or not, and if they haven't, they're kind of safe from binary effects. And we can then use the binary to measure various parameters like masses, radii, and so on, and actually confront single-star models. We want to look for post-mass transfer systems, rapid rotators, various types of strip stars, maybe merger products, things that will help us constrain binary physics. And last but not least, we want to look for those pesky black holes that are hidden in there and hopefully find them. I should highlight, if you manage to find a massive star and a black hole companion, this is arguably the most constraining system we have to tell us how black holes form or what kind of natal kicks they get. Because we know such systems form coevally, and the information that they store in their orbit give us very sharp constraints on how the black hole actually forms. So how did we come up with a sample? We have the color magnitude diagram of Gaia. There is a magnitude limit, which is pretty high. It's 16.5 to enable a certain data quality for the science we want to do. We look at stars above the 8 solar mass track here, which was computed assuming a certain set of assumptions. And you get to a count of about 5,500 stars. Out of these, we wanted to pick roughly 1,000 to probe this big parameter space of binarity, mass, orbital period, and so on. And this was done automatically. We basically wanted to have a homogeneous allocation across magnitudes, but of course these stars are very rare. We wanted to prioritize the high mass and bright stars, and this allocation then proceeded kind of automatically. Okay, so you can see that given our magnitude cut, we're more or less let's say unbiased in what we might call the O-star regime, stars above roughly 14 or 15 solar masses. But for the B-type stars, we don't really reach the ZAMS, okay? So we are missing a population there. Doing so, Flames is a multi-fiber spectrograph. It has a certain field of view, and these 8 fields are the fields of Bloom, okay? So they were automatically selected. Nothing here was cherry-picked. It was really coming out of the algorithm, these 8 fields, which kind of nicely trace star formation regions of the SMC. This is how the epoch coverage looks like, okay? So we started off with 9 quite dense epochs, then a few more, and finally we have these last 4, which cover the last year of data. This is sorry for the 8 fields that we have, okay? So they have similar patterns. And thanks Kunal, by the way, for preparing this plot. So in the first part of the talk, I'm going to talk only about this batch of data for which we actually published orbits, just like we have with Gaia DR1, 2, 3, and 4. On a smaller scale, we also had our first data release focusing on these 9 epochs. I'm then going to give you some teaser results for talking about the 21 epoch analysis. This is not going to be a separate batch of paper. We're going to include the 4 epochs as well, but they haven't yet been reduced. This is really fresh. So I'm only going to give you some preliminary results coming out from these data. Okay, first thing we did when we got the data, we wanted to classify the stars and characterize the sample spectroscopically. This was a big effort led mostly by Paul Crowder, and we thank him for that, wherever he is. And the HRD that you see here was constructed from spectral type calibrations. Okay, so we have our spectral types. This is why you see these strips. It's going to improve in the future, but for now, this is how our HRD looks like. And this sample is quite heterogeneous, so let's see what it contains. We have roughly 140 O-type stars. Okay, so these are the more massive of the bunch. I hope you can read roughly the masses they trace between roughly 15 and maybe all the way up to 70 solar masses. We have roughly 300 B-type dwarfs, thought to be still on the main sequence, perhaps with some exceptions. Then we have this mystery sample, okay, the B-type supergiants, a very big sample. For those of you who have attended Norbert Langer's talk 2 weeks ago, he already presented this. This has been known also for decades. We see tons of stars in this region, but naively we don't expect them. Okay, if you look at the underlying tracks, you will see these dense points. Maybe it's hard for you to see, but there are these dense points which are equidistant points. Where you don't see any points, that's where you don't expect any stars. This is the Hellsprung gap. But we see a ton of stars in there. They're real, and they're probably binary interaction products, but maybe our models are also not well calibrated. Then we have this other mysterious group, the yellow-ish supergiants. Not all of them are that yellow. These are bluer. We have quite a lot of them as well. Again, we don't really understand what they are, okay? Knowing the binary properties of these samples is crucial. And finally, we have the OE and BE stars, rapidly rotating stars with disks. We can spectroscopically identify them. Literature massively suggests that many of them are post-interaction binaries, previous mass accretors. It makes sense to separate them and look at their binary properties separately, which is why they're separated. Not going to talk about all of these populations in detail, but just to give you an overview. Also, we have some cool stellar exotica. Remember, the sample was not cherry-picked, yeah? So we have we identified 3 magnetic candidates. You can tell by the way their spectra look. 3 B bracket E supergiants. We had some cool discussions about them last week. 4 high mass X-ray binaries, and 2, what we think are bloated strip stars. These black hole imposters were suggested. So already these numbers are quite interesting to consider, but this is still preliminary. Okay, for the first batch of 9 epoch papers, what we did is, since these 9 epochs were not sufficient for a full orbital analysis, is a simple binary classification criteria, yes or no. We call something a binary if the radial velocities that we measure exceed a certain significant threshold, typically set to 4 sigma, and we want the peak-to-peak threshold to exceed a certain value, typically set to 20 kilometers per second. This comes to try and avoid false positives coming from pulsations and stuff like that. So one could argue about this, but these are typically the criteria that are selected also historically. So such a star you would call a binary, see very clear radial velocity motion. Such a star you would call a single star in this analysis. We do this for the O-type stars. Okay? I remind you, this is the first time we're actually exploring multiplicity systematically at low metallicity. We didn't know what we will find. Lo and behold, we find a high binary fraction. We measure a binary fraction of 45%. This is not the true binary fraction because we have biases. We only have 9 epochs covering about a month and a half of data. We have limited spectral resolution, limited spectral range. We need to correct for these biases. To do a bias correction, kind of like the LIGO people, we need to assume certain power laws, certain underlying distributions. If you do that, you find an intrinsic binary fraction of 70%, very close to the famous number that was reported by Usana and others in the galaxy. You can actually also fit at the same time for what is the best power law index for the period distribution. What you basically get, this 0, means that it's flat on log P. Again, something that's quite famously observed for massive stars. So no surprises, except for the fact that massive stars at low metallicity seem to behave very similarly to how they do in the galaxy. So if you consider metallicity trends, this is a well-known trend that has been known for low mass stars. As we go to lower and lower metallicities, the binary fraction of low mass stars seems to increase, has something to do with star formation and binary formation. If we look at massive stars, we have only 3 data points: Milky Way, LMC, SMC. This is the Bloom data point, large arrow bars. Cannot say much except of the fact that we see a persistent high binary fraction. I should mention this is a paper that, together with Uksana and Julia Bonensteiner, we recently published. Yeah. Okay, we did the same for the B-type dwarfs. This was work led by Jaime Villaseñor. Observed binary fraction 49%. Again, very high, but actually B stars are even harder to detect in this sense for motion because they have typically less signal to noise. If you correct for biases, one actually finds an intrinsic binary fraction of 85%. Okay, so reaching as high as that. And you can look at the same diagram as before, this time plotting this 85% on this diagram. Okay, you can argue if there's a trend or no. I wouldn't rush to any conclusion. Hopefully with the full data set, we could shrink these errors and maybe say something more meaningful. All we can say for now is that it's probably a safe bet to say all massive stars are binaries, also atomic abicity. Okay, now we move to the mysterious blue supergiants. Remember, we don't know what these objects really are. Nikolai Witowski led this work, reported an observed binary fraction of 23%. Okay, so we see, at least in the observed fraction, a drop. Intrinsic binary fraction, now it gets pretty risky because you need to assume underlying distributions. If we don't understand what these stars are, it's harder also to correct for our biases. But being brave and doing some assumptions, Nikolai computed an intrinsic fraction of about 40%. Actually, this sample is pretty interesting because it lies more or less where massive stars and the main sequence, okay? And some of them could be still on the main sequence, some maybe are not. They can really help us tell when stars actually finish the main sequence. That's not something we can shift the terminal age main sequence based on certain assumptions in the models. And this is one first attempt in doing that in this sample by Lennon and Danny Lennon in our group. Basically, they measure the rotational velocities of the sample and of all the stars, and they note a sharp drop beyond a certain regime, okay, that they plot here as a function. This is for given temperatures, for given luminosities, they have different temperatures. You can translate this basically to a regime on the HRD where you see this sharp drop. And this seems to be telling us that potentially the terminal age main sequence lies somewhere here, where we now want to do this one step forward to combine the binary physics that we know, the binary properties that we know about the sample to actually empirically constrain where the terms of this region lie. So this sample is probably a mixed bag of main sequence stars and weird post-interaction stuff. And finally, we have the yellowish supergiants. This is work led by Lee Patrick. These guys have a lot of absorption lines, and we can measure the radial velocities extremely precisely. And when you do that, you find peak-to-peak. This is the histogram of the peak-to-peak radial velocities. If you would take the standard 20 kilometer per second threshold, you would conclude that there are no binaries in this sample. But perhaps this threshold should be lower. After all, these stars are very big. They probably cannot accommodate very nearby stars. There's a whole debate in the paper about this. So what we can say is that there is a deficiency of relatively close binaries, and I'll talk about this more in a second. Let me try and take this in one kind of global picture, what we actually see on the HRD. We start with a very high binary fraction for the progenitor stars, and as we advance in evolutionary phase, we drop to virtually zero, according to the 9-epoch analysis. You might say this is obvious because the stars expand, they swallow more and more space, they allow for less configuration space to actually reside, or less companions to reside next to them. But if you would just assume, say, that yellow supergiants are the result of some slow expansion of a massive star, we should have still, and this is done in the paper that discusses this, we should have still detected companions given the distributions that we know for massive stars. So this drop probably tells us that this population really comes from some kind of a post-interaction effect. And I'll give you some more teasers about this population in a second, because for them, the new data are really crucial. So yeah, this brings me to this was the 9-epoch results, but now I'm going to give you some spoilers related to the full epochs. So what's the power of 20 epochs? And here I want to give also credit to 3 of my students who are really doing a lot of work here, Zava Katabi, Roy Vadia, and Tom Sayada. We have so much science we're doing now, together with the entire collaboration, and I won't have time to cover it, and it's also not really the topic of this work. we're going to get, basically for all the binaries, unimodal orbital solutions. We will get orbital parameter distributions. This is just an example for the period distributions of the blue supergiants. Okay, but I'm not going to talk about this today. We can explore tides. So this is, for example, a plot showing the eccentricity versus period of double-line spectroscopic binaries. There's lots of physics in here, but I want to focus on some cool catches that we have and mainly then get to the black hole search. One thing that these number of epochs allow us is to go past this standard 20 kilometer per second threshold that we usually use. Okay, this is an example for a binary that if you just see the first 9 epochs, even though I plotted a kind of a sign here so it's clear that there is a periodic signature, you would not call it a binary. It would not pass your criteria. But now we have all these epochs and it's absolutely clear that there is a period in there. Okay, and basically this allows us to probe more extreme mass ratios and get to longer periods than we could before. To show you some cool example, this is a blue supergiant that previously did not pass our binary criteria, has a radial velocity amplitude of 8.7 kilometer per second, but a very, very clear periodic behavior here. So we're finding new binaries. This is a more extreme case, a radial velocity amplitude of only 5 kilometers per second. Here we really want to get the last 4 epochs, but it passes our significance criteria. This is a yellow supergiant. Again, radial velocity amplitude of only 2.5 kilometers per second, but passes our significance criteria. And again, we are eagerly waiting for the last 4 epochs to verify this. And this is the most extreme example that I've seen so far. Radial velocity amplitude of only 0.7 kilometers per second. You may say, okay, I don't really trust this. But interestingly, this guy does have a UV bright companion. So we see that it has UV excess. Okay, we don't know that it has we don't know what the companion is. So these are just some sneaky examples, and there are many to show. So you may wonder what kind of mass ratios and periods we're sensitive to. This is very preliminary. It should be roughly correct, but it should be done more accurately. Because we're so sensitive, for example, for yellow supergiants, where you see yellow in this diagram, this means basically a detection probability of 1. So we can probe extreme mass ratios as extreme as about 1 to 50 with this kind of population. For OB dwarfs, more like 1 to 10 or so. So we had some interesting chats about extreme mass ratios. So these are the sort of regimes we're sensitive to. Okay, I have some more time, good. So now we get to the actual topic of this workshop, black holes. How do we find those pesky black holes in the sample, and how do we do generally? So we already heard some cool talks about this from Kunal, from Reese, and others. Basically, in a spectroscopic survey, you want to be looking. Oh, I have to open my volume here. Oh no. Sorry, I put so much effort into this. Matthew, don't hate me. Oh no, now I cannot. I don't know how to do it. Oh. Because I'm connected, I don't know how to do this. Okay, I'm not gonna ruin the conference for this. I'm sorry. You'll get your private. I forgot to put the volume on. Well, in a spectroscopic survey, we're looking for single-line spectroscopic binaries. Okay, so basically stars that are moving around something we cannot see. Okay. And so we already heard very nicely some talks by Reese and by Kunal about how we can actually deal with this. How can we tell if there's a luminous star in there? Various approaches of how to deal with it, but if you want to go agnostic, spectral disentangling is the choice. And here I put some techno music, but my volume is off. Sorry, I put so much. Spectral disentangling, in case you didn't catch it in the previous talks, is a method where you plug in your multi-epoch spectra and mathematically extract the 2 best residual spectra that reproduce these multi-epoch data. You can do a lot of cool stuff with this. Mostly, you can also tell if a luminous star is in there or not, and if it's not, find your black hole candidates. So to show you a very quick example, which was already mentioned by Kunal, this is a study we implemented this technique successfully in the Tarantula Nebula. This is a sample of 51 single-line spectroscopic binaries. Here you see the orbital periods. Here you see the companion masses. How do we know the companion masses if we don't see them? Orbital dynamics, right? We have the Newtonian dynamics and we have estimates for that. masses of the donors. We don't know which ones are the black holes here. It could be this one, could be that one, could be this one. We implement spectral disentangling, and lo and behold, everywhere where you see a green star, this is where we actually retrieve a companion. So Lika, you asked before, what can we do with all these cool companions? They typically probe the more extreme mass ratio regime. So they help us find binaries in a more extreme mass ratio regime, and we can actually populate the mass ratio distribution, and we did that in that paper, for example. Okay? So they're usually not that mysterious, they're simply faint stars. We do that, we clean all the sources where we find companions, and we are left with this sample. Again, this was shown by Kuna. The obvious target that pops here is this guy. It doesn't show a companion, but it has a high minimum mass. We disentangle it, we see nothing in the spectrum. This was also studying Karim. I was involved, I don't know if he's here, but we invited him so that he cannot kill the black hole afterwards. And we reported a black hole in the system. This system is especially unique because it has an eccentricity of virtually 0, which tells us that however this black hole formed, it must have formed with a negligible kick. Okay, so this is one of the only systems where we actually know the mass of the black hole, we know the kick history, and we can say some cool stuff about it. So coming to Bloom, do we see such systems? So this is super preliminary, and I have no concluding results to show you. I apologize for this. I asked my students, so this is not homogeneous, I'm sorry for that, to prepare such plots, yeah, where we have periods versus a secondary mass. And the dashed lines that you see here, the upper dashed lines, these are the 5 solar mass thresholds. And all I can tell you is that we see a bunch of stuff. these are SB1s, okay? So these are SB1s, so single line spectroscopic binaries in the O-star sample and blue supergiant sample. And you can see that there are a bunch of stars in here. If you count the number of stars above 5 solar masses, you get 10 candidates in each of these samples. Doesn't mean they're a black hole. We still need to do some disentangling for this. What we do not see is a 33 solar mass black hole, like Gaia black hole 3. So we're going to have a bit of a harder time. What, this guy? Yeah, with the error. yeah, maybe. Generous errors. Yeah. Okay. One final candidate I wanted to mention. This actually comes from a sample I haven't talked about. Julia Bodensteiner is analyzing this one from the BE sample. There is one cool star. It's a hot star, but it's cool in its way. This is the historical light curve of the star. So you could see it was pretty flat, and then suddenly there was an increase in the light. This is associated with the disk of the BE star suddenly emerging. You can actually trace this spectroscopically. And as the disk suddenly emerged of the BE star, this happens, the disks of BE stars come and go on timescales of decades. Suddenly you start seeing these peaks in the light curve. And when you look at the radial velocities we get from Bloom, this matches, okay? So we see the orbital motion, and we see these variability also happening. We can constrain the minimum mass of the companion, 3 solar masses. We don't know what it is. It could be a strip star. It could be a black hole. We did look for X-rays. We had 0 detections, like only an upper limit. So we're not sure what that is, but it's an interesting candidate to follow up on. I'm done. Before I'm done, I want to make a shameless commercial for the KITP workshop that we're organizing. If you're enjoying this workshop, wait until you see our workshop. And so there's still some time. It's only happening in March and April. It's going to be about massive stars and supernovae. It's organized together with Yair Arkavi, Jared Goldberg, Ilva here, and Andy Howell. Application deadline is January 30th, so there's still some time, but I think basically all of you should be interested in this, and I encourage you to apply. So I guess I will just leave you with this kind of rough summary, and I'm happy to take any questions.
Thanks, very nice talk. Can you go back to your slide about the V sin I for blue supergiants?
V sin, yeah. Mm-hmm. It's quite a journey there.
Yes, here. Okay, sorry, I find it a little hard to understand the x-axis here. What does that mean? This log TEF at log.
Yeah. So what this means, or what this plot is showing, is basically the authors the main authors, try to identify where a statistical drop in V sin i's happens, and this happens for different luminosities for different temperatures, basically.
Yes.
So this literally corresponds to the diagonal on the HRD. Okay.
Oh, so you just switch the axes.
Yeah, I guess.
I see.
Yeah. Yeah, you can if you want, you can ignore this plot and just look at that plot.
Okay.
And
yeah.
this is more or less where they find the drop.
But the y-axis is the V sin I, it's not luminosity.
Yeah, sorry.
Okay.
The y-axis here is V sin I, exactly. So you see very rapid rotators, and then suddenly the rotations stop.
Okay, so how confident are you like these V sin i's are actually rotation other than like macro turbulence for these massive stars?
So these authors look into this quite heavily, and they account both for macro turbulence as well as V sin I.
Okay.
Using Fourier approach and other methods.
Yeah, sure. Thank you.
Okay, so for the spectral disentangling, you're using a library of spectra to do the disentangling?
No, it's fully agnostic.
It's fully agnostic, okay.
At least in our approach. There are as Reese suggested, there are different approaches. Some of them can be less agnostic, let's say, but this approach that we use is fully agnostic.
Oh, okay, all right, good.
Question?
Hi, great talk. I should know this, and maybe we talked about it, but are there legacy surveys, like for example, Chandra of the LMC? And have you guys searched for, instead of being motivated by Bloom to look for archival photometry or X-rays, have you done like systematic cross matches to say we have this many, B supergiants, this many class of stars, how many of them are X-ray sources, and looked at that?
Yeah, so we have done that. Unfortunately, I don't remember too much the results, but in paper 1, we actually do have exactly such a cross-match with X-ray catalog, and there are 8 sources that show some X-rays, 4 of which are identified X-ray binaries, and the others are not so clear. So we have done such a cross-match, but I don't remember the results from the top of my head.
Okay, one question over there.
Thanks for conducting such an amazing survey. I know they're not black holes yet, but are the candidates that you have showing any differences in terms of the population?
I'm afraid it's simply too early to say anything. I've hardly seen this, myself, the candidates, and I don't. We can look at them on this diagram, but I cannot say anything that would make sense right now. But these are questions we need to look into once we look into them. So you consider orbital parameters, and then, I mean, not much we can say at this stage. Okay.
Hi, Thomas. You said there are 2 candidate puffed up stripped stars in your sample. Can you say a bit more about their properties? Do they look similar to the galactic ones, their orbits, eccentricity?
Yeah, so again, this is something that is just coming from preliminary analysis, and so not too comfortable of saying too much about them. Basically, they were identified by, we already have intuition for this, right? You see these rapidly moving narrow line stars, and you see some kind of thing that is infilling with emission. From what I've seen for the orbital fits and stuff like that, they look similar to what we know from the galaxy, but we still didn't get to the point where we actually compute masses for them. So again, I have to disappoint you and say you have to stay tuned for this.
Thank you, Tomer. I enjoyed your talk a lot. I have a question about the low metallicity sample. You told us that basically the binarity fraction is similar or even higher in some cases, and that the period distribution, I think you said that it's flat, but maybe I missed that. So from what you can tell so far, does it seem that the orbital parameters, period, eccentricity, and so on, mass ratios are similar to the current galaxy or to our galaxy, or low metallicity behave completely different?
From what we've seen so far, this is still pending, but from the 9-epoch analysis and from all the evidence I've seen so far, there is nothing obviously different in this population compared to the Milky Way. Okay?
One thing that was catching my eye is that here you have a slight preference for a positive slope of the period, while in the galaxy, a slight preference for a negative slope, no?
Okay.
But
yeah,
it's not statistically significant.
Ug maybe should comment on this because he actually ran the statistical.
That's the best fit we derive, but as Tomer was saying, it's based on Rajah velocity amplitude variation, while now for many systems we do have periods, and I would like to see this plot at some point in the next few months. What's the uncorrected, or bias uncorrected and bias corrected period distribution for the O stars and for the B stars, but based on actual period measurements. That being said, you should anyway don't pay too much attention, because in a range of minus 0.05 to plus 0.05 for that exponent of the log P distribution, it seems like a big shift, but it actually doesn't change a lot in the actual case A, case B, case C, except for the very first few days of the period distribution. So it's interesting, but I think the first order of magnitude is that there's no reason to change your population synthesis assumption yet.
Thank you, Tomer. I'm curious about the last things you showed with the V sin I distribution and potentially the end of the main sequence, because it was overplotted with some models. Those models, do you have a feeling for what the overshoot is? Is this the Hastings models or Abel's models?
No, but you'd have to help me here. Do you remember?
Yeah, that's Abel's models, and I think their overshooting is somewhat smaller than in the bot models, for example, which is 0.3.
This is the 0.2.
Yeah, something like that. And if you use 0.3, you get pretty close to the red line, actually.
Right. Yeah. Okay. That's nice. So this wasn't already the 0.3. Okay.
Yeah. This maybe suggested there is a huge mismatch, but this is indeed a very specific set of models. And
yeah, on the overshooting, of course, when you look at observations of individual systems, either astroseismology or eclipsing binaries, people find a whole distribution of core sizes from very small numbers, close to 0, to quite high numbers like 0.5. So this might be the average, but per mass, there is no such thing as the times.
possible.
Yeah. Do you see any stars that have abundance anomalies?
Again, you guys are asking a lot of questions for which we don't yet have real answers.
Well, because you already told us the stuff where you do have the answer.
Yeah, you do see a lot of indications in some stars for enhanced nitrogen. That's very obvious. But none of these stars have yet been analyzed spectroscopically to get your abundances. So still in prep. We want to get the binaries first, and then you can do a proper analysis.
I also have a question. So you have the V sin I's and you have orbits based on the 9 epochs. Are there any SB1s where the star that you see in the spectrum is faster than tidal synchronization?
I'm sure there are. Not easy for me now.
You're sure there are?
Yeah. Yeah, wow. I'm pretty sure there are. Cool. Yeah, because I've seen some example. So
the reason I'm asking is because there is a small galactic sample of stuff like that. And so I was wondering, like here at low metallicity, you have presumably less wind mass loss rate, less spin down, so it should be easier to find them.
So you mean where we see rapid rotation that is above the synchronization?
Yes.
But yeah, I mean, but you mean in a certain period range or what?
No, actually, I was not going to constrain you on the period only. Then I would ask about the mass ratio
Of
first.
course, all these rapid rotators, I mean, they're not necessarily in short period binaries, these guys. Okay. So, yeah, mass accretors, right? Are we surprised?
Oh, maybe. It depends on what's the companion. Then have you spectrally disentangled them and found the strip star?
Yeah. Yeah. I maybe just a bit related to this question, I haven't talked about this, but we have this eccentricity versus period diagram. And one thing that is interesting to note is while these red arrows are upper limits, so we see that the majority of stars up to a certain period are circularized. There are some, and especially, for example, this system, short period eccentric. This system, short period eccentric. So it's not exactly related to your question, but maybe it is.
Do you know what is the companion to that short period eccentric system?
No, not yet. This is all super preliminary. Sorry. I'm so sorry. Next year.
Okay, so when you go to 50-to-1 mass ratio, some of those companion stars should be pre-main sequence stars, right?
Potentially.
Okay. So you don't, okay, that kind of answers my follow-up, which is, do you see any evidence for disks around the companion stars or anything like that that might indicate that they are?
I think at this stage it's more like we should think about this, should be aware of this possibility. I'm not aware of anyone having reported in this sample so far something that looks like a pre-main sequence.
Okay.
Are there proper motion data for all your fields?
Yeah, so that's actually work I haven't mentioned by Mitchell Stoop, who is not here. He's using the radial velocities together with proper motion data to look for runaway statistics. And they find runaways. But more than that would be a bit hard to summarize. But yeah, there are proper motion data, and they are robust, especially for the brighter stars. Yeah.
There are no more questions. Maybe we can thank Tomer for a great talk.